Okay, this is Giancoli Physics, 7th edition AP edition. We are working in Chapter 10, Fluids, and we're on problem number 26. Go ahead and dive in. Problem 26 reads, you have a spherical balloon that has a radius of 7.15 meters and it is filled with helium. How large a cargo can it lift, assuming that the skin and structure of the balloon have a mass of 930 kilograms? Neglect the buoyant force on the cargo volume itself. So go ahead and pause the video, chew on that problem for a bit, see if you can come up with a plan. Come on back when you're ready. Okay, as with most problems, we're going to identify the numbers we're working with here. We have the radius of the balloon. I'll just use R. It's the only radius we're dealing with right now, so we're just going to use a single capital R with no subscripts. We have a mass of the balloon and its structure, so we'll use M subscript B for that one. And what they're asking us is how large a cargo can it lift. Now, the word large here would imply volume normally. However, given that we know nothing about the density of the cargo or what material it's made out of, with this sort of problem, the best we can do is find the mass of the cargo. And so we're going to assume that's what they meant by saying how large. Because again, without density information, we're not going to be able to determine any physical dimensions about this cargo. So we'll go with that. A picture often helps. So I got a large spherical balloon. It's holding up what is presumably a dimensionally small cargo here because they told us to ignore the buoyant force on the cargo itself. So we're assuming it's small relative to the cargo. And another useful thing here is a free body diagram. Because what's happening is this balloon is pushing air out of the way. It's displacing a lot of air. The gravity acting on that air that has been displaced is pushing back on the balloon, creating lift on the balloon to offset the weight of the cargo. Again, this is an example of Archimedes' principle. So I've got the force of gravity pulling down on everything involved there. We'll talk more about that here in a second. And then I got a buoyant force pushing up here. These two need to cancel out in order to carry that load. Now we can go through a formal Newton's second law analysis here, set up F equals ma, sum of forces on the left, set these two opposing forces, positive buoyant, negative gravitational, equaling a zero acceleration. Then these two would end up equaling each other. However, we can go ahead and just start right from there, especially considering that the force acting is going to be the mass times the acceleration due to gravity. So the acceleration due to gravity is also going to cancel out. Really, all we need is for the mass of all these items being pulled on by gravity here to be offset by the gravity that's pulling on the displaced air. As long as those offset, then we'll be able to float our cargo. So again, there's a bunch of preamble here with Newton's second law, but if you want to start right here, this is fine. That's not M sub B. This is the mass of the buoyant force, so we're going to call that mass sub A for the air, since we're already using B for the balloon. But the buoyant force is created by acceleration due to gravity acting on the mass of the air that has been displaced. And that's going to have to offset the mass of the balloon itself plus the cargo. And we actually also have to account for the fact that the balloon isn't actually empty. The balloon does have something in it, in this case helium. Now, if you look at a table of densities or look these up, you'll see that helium is only about 10 or 15% of the density of air, so it's definitely lighter than air, but it's not statistically insignificant. So it does have an impact to a fair number of significant figures here. So we do need to account for the mass of the helium as well. We'll add that in there. Now again, gravity is acting on all these things. We used pre-eliminated gravity and canceling out on both sides. So now for the mass of the air. Since we know density is mass per unit volume generically, I can replace any of these masses with the corresponding density and volume. So in the case of the air, that is certainly something we want to do. We don't have the mass of the air that's displaced. but we do have figures we can look up the density of the air. I can calculate the volume of the air based on the dimensions of the balloon. The mass of the balloon is a number I have. The mass of the cargo is a number I'm looking for. Then the mass of the helium, much like the air, I don't know that mass, but I do know its density. And it's going to have the same volume as the balloon, or the air, which is the volume of the balloon. So I can use that volume for both the helium and the air that's displaced, because that difference here is providing the lifting force to offset these masses here. Don't quite have all these in numbers that I know yet, so let's go and replace that volume. Volume of the air is 4/3 pi radius cubed. And for better or worse, I have that in 2 locations. Now this looks like an equation where the thing I'm looking for here, the mass of the cargo I can lift, is the only number I don't know. The rest of these are numbers that I have. So now I can rearrange. As per usual, I'll take as many steps as you need. As you get more proficient, you'll be able to do this much quicker. For me, I want this mass by itself, so I'll move the mass of the balloon to the other side, so that'll become negative. I'm going to move this, effectively the mass of the helium, over to the other side, factor out the 4/3 pi r cubed, and just get the difference of these densities. So the mass of the cargo that we can lift is going to equal, now the mass of the balloon is going to end up being a negative, so I'm going to save that until after I get the positive stuff in. On the other side of the mass of the cargo, I have the density of the air times that 4/3 pi r cubed. Again, I want to factor out that 4/3 pi r cubed times the density of the air, because when I move the mass of the helium over, I'm going to get the rest of that expression with the same coefficients up front with the radius cubed. And then moving the mass of the balloon over as well, we get that relationship. Again, we know all these numbers, so we can go ahead and plug them in now. Again, just conceptually, this is the difference in the densities between the helium and the air, multiplied by the volume of the balloon, will tell us how much mass difference there is here that can provide a lift. The balloon itself offsets some of that, and any surplus that's left over will be the mass of the cargo that I'm able to lift with this balloon. Let's go ahead and put our numbers in, see if we need any unit conversions. I didn't identify any right out of the gate. Our radius is in meters, so that looks good. 7.15 meters cubed. The whole value cubed, not just the meters. For the densities, look them up on the internet or use the table from your textbook. Density of air, 1.29. That's kilograms per cubic meter. Notice no times 10 to the third here. We're talking about air, so it's much less dense than the water and other things we're used to dealing with. Then the helium, and even lighter or less massive, less dense, 0.179 kilograms per cubic meter. Move our densities out of the way here. And now we subtract off the mass of the balloon that we are already required to lift, which is 930 kilograms. As always, before we pick up our calculators, we should know what the calculator is going to tell us. The 7 cube number here, that's 7 times 7 is 49, so we a little bit more than that, even higher than 50, but we'll round it to 50. Times 7 again, you're looking at 350, but again, we're rounding down, so let's go and round that up to even 400. With that 4, it gives us 1600. Pi and 3 is about a wash, so that's about 1600. These figures here are a little more than 1. So times the 1600, just call it even, maybe 1900, 2000, something like that. Minus these 930. We're looking at something near but less than 1,000 kilograms lifting mass for the cargo. So let's go ahead and punch those numbers in and see what we get. Okay, as expected, our calculator spit out a number of about 771.065 kilograms, which again is in the vicinity of that mental math figure we calculated of just under 1,000. We can live with that. As far as significant figures go for this problem, it looks like everything we have is in 3 significant figures. Let's go ahead and round our mass to an appropriate number of 771 kilograms. That's the mass of the cargo that this balloon can lift if it's filled with helium. That solves this problem, and we're ready to move on to the next.